Okay.
All right. Hello, everyone. Thank you very much for coming to this very first NetPlace seminar in this semester. And today we have Federica is going to talk about weighted simplicial complexes and their representation power of high order network data and topology. Thank you very much, and the times are yours.
Okay. So thanks, first of all, for the opportunity of presenting my work in here. So as you might have read in the abstract and in the description of the workshop, of the, not the workshop, really, of the seminar, I will first talk like of this work that I've done in collaboration with these people you see listed here. And then at the end, I will share a few slides about what's like doing a PhD in Italy, which I hope will bring a nice discussion out of this talk. So let me start with this technical part by telling you that this work is about how to find a way to use simplicial complex representation to analyze and process higher order interactions without losing information. I'm going to clarify what it means later. So let me introduce some terminology. I don't know if you're already familiar with it, but anyway, I will be brief and concise, I hope. So a first step in the understanding of a system of interacting objects is that of considering not only pairwise interactions, of course, but also many-body interactions, so simultaneous interactions occurring among a set of more than two objects. The hypergraph or higher order network is the object we normally use to model this situation. So instead of having a set of edges here, you have a set of hyperedges, which is nothing more than an arbitrary non-empty subset of V. So a hyperedge is an arbitrary non-empty subset of V. So a simplicial complex is a subclass of hypergraphs, which is less general in the sense that the hyperedges that form a simplicial complex have to satisfy the property of being closed under inclusion. What does it mean? It means that given an hyperedge of cardinality, for example, 3, which is a 2 simplex, a triangle, as you can see in this slide, you have to consider to include in the hyperedge set, which is the set of simplices for simplicial complexes, also all the pairwise interactions and all the single nodes, of course. Okay, so this is named property of being closed under inclusion of simplices. Now, now in this slide, I want to show you that the simplicial complex representation can be slightly less general than the generic hypergraph. And why is that? Because, for example, if you consider this example, which is a very toy example coming from the area of collaboration networks. So suppose you want to consider a collaboration network referring to two papers whose authors are respectively listed here. Now, if you want to build a hypergraph, you could think of building a hypergraph made of authors as vertices, and then the hyperedges might correspond to the papers. So you have a hyperedge for paper 1 and then a hyperedge for paper 2, and that's it. In the simplicial complex representation, instead, what you have to do to satisfy the property of the hyperedge set of being closed under inclusion, you need to include also all the subsets of every hyperedge, namely simplex. Indeed, for example, here you have that the edge BC is there because there is actually a paper, a two-author paper authored by just the two of them, so author B and author C. But for instance, you give the same importance to the edge AC, even though A and C did not co-author a two-author paper together. So in this sense, the hypergraph appears as a more general and more faithful representation of the information you have about the higher order collaborations here. And the simplicial complex as it is, so in this unweighted version, does not allow to fully reconstruct all the original information about what groups of authors co-authored what paper, okay? So the question is this one: are simplicial complexes a less powerful representation of higher order data? Well, the answer, of course, will be no, but with specific specific weights that we are going to add. So as I said, the higher order network is more general than the simplicial complex at a glance. And but at the same time, we could be interested in using the simplicial complex representation because, as you might have heard and like you might be familiar with, the simplicial complexes are a geometric concept, which turns out to be very useful when studying the topology of the network and the propagation of, for example, of dynamical signals through the networks. So it is sometimes useful to define some topological weights assigned to each simplex, so to each hyperedge of the simplicial complex, in order to faithfully represent the information contained in the higher order interactions. And this will be exactly our solution. So we will introduce some choice, some assignment of topological weights to the simplices, so that the original information about the higher order interactions among the objects you have can be fully reconstructed. Okay, so there will not be a loss of information, and at the same time you will be able to use topological and algebraic geometry concepts to unveil topological properties of the network. So let's see how to best choose such topological weights. The idea is pretty simple. So suppose you have a network with some bare affinity weights given. So in the example I've shown you before about collaboration, it can be, for instance, the number of papers that a team of co-authors contributed to. Okay, so we are going to refer to these input weights, let's say, as bare affinity weights, and these normally come with the input data. Of course, this includes also the unweighted data case. So in that case, we assume that the bare affinity weight is 1 for edges that are included, of course, in the higher order network, and 0 otherwise. Now, the assignments work like this. We start by simplicial complexes of maximum order, meaning that, for instance, if in a simplicial complex of order 2, maybe I forgot to say this, a simplicial complex of order 2 considers at most triangles, so triadic interactions. So this is an example to explain the assignment referring to a simplicial complex of order 2. So let's start by some bare affinity weights, okay, the green ones, assigned to the triangle. Then we proceed starting from the simplices of maximum order, so triangles, and then go down till the simplices of order 0, which are vertices. How we do the assignment? The topological weight assigned to the simplices of maximum order, so the two triangles, is equal to the bare affinity weight. Okay, so indeed, here the red indicates the topological weights, and is equal to the bare affinity weight. Then we pass to the edges, and then each edge is associated a topological weight, which is equal to the sum of the topological weight of the simplices of higher order that are incident to that edge. So in this case, just the triangle is incident to, for example, edge AC, and the bare affinity weight of the current edge, so 2 in this case. So the topological weight of this edge will be 7. Same for the other edges. And of course, the same for the nodes. So the topological weight of a node will be the sum of the edges that are incident to that node, of the topological weights of the edges incident to that node, plus the bare affinity weight of that node. Okay, so it's an iterative process, which is pretty intuitive and simple. Notice that everything is linear here. So starting from the simplices of maximum order, in this case triangles, and starting from the topological weights, so the red ones that we just assigned, we can go back the same way we went onward to assign them, to reconstruct the original weights, so the original bare affinity weights. Okay, and this is the advantage of having this weight assignment, besides other advantages that we'll see later. Now, to show you a possible use and a nice application of this weight assignment process, I'll talk to you about how to exploit the simplicial complex representation, and in particular the weighted simplicial complex representation, to model higher order collaborations in the field of network science. In particular, we made our own data set referring to nearly 700 journal articles of 5 years in this period, whose metadata contain the expression multi-layered network. The data, based on the number of the distribution of the number of authors for each paper, were encoded in a simplicial complex of order 2. So we included hyperedges, at most formed by 3 vertices, so triangles again. Okay. Now the nice thing is in this application is that by generalizing a widely adopted classical bare weight assignment for collaboration networks, it turns out that with that, using that convention of bare affinity weights, you can, the topological weights result having a very nice property that we will see in a minute. Now, let me first tell you what could be a convenient way of assigning bare affinity weights, so the green weights that we have seen a couple of slides before. The idea is to choose these bare weights following the idea proposed in 2001 by Newman, who suggested a very widely adopted convention for weighting collaborations. So the original reasoning that Newman made was this one, where this here. So, so the idea is that an author of a paper with nk authors shares his collaboration equally among all the with all the remaining nk-1 authors. Okay. So what we do is simply to assign weight 1 over nk -1 to each edge linking the author I to each co-author. Okay, this is very, very simple, actually very intuitive. I don't know if I clarified that, but this what's important is that this weight assignment has a nice property. Namely, if you sum the edges that are incident to a vertex, so an author, it gives you back the total number of papers written by that author, which is very nice. What about triangles? So the idea is to reason in an analogous manner. So author I in a triangle shares its collaboration with all the possible pairs of other co-authors, okay, of the paper K, which are exactly nk-1, this binomial coefficient, okay. So following this idea, what we have is this couple of formulas for the bare weights. I'm not going to give you the details, but they can be obtained from the idea that I shown you before. If you want the detail, by the way, you can check the paper. And the nice thing, as I was anticipating, is that the resulting topological weights, so the one we compute iteratively, here indicated in black in this example, turns out to have the nice property that the sum of the weights, of the topological weights of the edges that are incident to a node is exactly the total number of papers that author contributed to, which is very nice and very interpretable. And also, as I mentioned before, if you assign these topological weights, then you can recover to the bare weights that you assigned, which are here indicated in blue. Okay, so here is an example of the computation where the edge AB is 0, because basically you consider A and B did not contribute to any two-author paper, okay? While edge BD is assigned weight 1 because they contributed to a one-author paper. The fact that edge BD and also edge AB contributed to a three-author paper is then encoded in the triangle bare affinity weights, okay, which is computed here following the second formula here. As you might see, can see, for example, author D co-authored two papers, this and this. And if you sum the weights of the edges incident to D, which is 1/2 plus 3/2, it's exactly 2. So the number of papers author D contributed to. Okay, so observation, of course, if you're only interested in the presence of absence of a collaboration, it's enough to assign bare weight 1 to each D simplex that you include, and then proceed iteratively to assign the topological weights. Okay, so in the end, our simplicial complex is a less powerful representation of higher order data. With this choice of topological weights, you can fully recover the information you have about the input bare affinity weights. And so in this case, simplicial complexes turn out not to be less powerful than general higher order networks, and they can be used interchangeably with hypergraph, in fact. So, but beside the advantage of being a faithful representation of the higher order interactions, they bring also some other advantages related to the spectral analysis of the higher order interactions. So in particular, this choice of weights allows to normalize the Hodge Laplacian, which is the higher order version of the graph Laplacian. That's a very useful object when you try to explore the spectral properties of a graph, and in this case of a hypergraph of a simplicial complex. And the nice thing is that with this topological weight assignment, you can normalize the Hodge Laplacian, which is computed at every order of the simplices. So it's computed at the level of nodes, at the level of edges, at the level of triangles, and so on. And thanks to this fact, so the normalized spectrum allows to compare spectral properties, and in particular, we will see higher order diffusion properties of the network at different dimensions. Okay, so you can study, for example, how information flows through the network at different levels. Okay, and here in particular, we will see in the network, in the collaboration network, simplicial complex, sorry, that I've shown you before, how to study the properties of higher order diffusion processes with a generalization of the von Neumann entropy. So the von Neumann entropy, in brief, was introduced to study information encoded in the spectrum of networks, and it's not much different for some aspects from the Shannon entropy. And it's, of course, defined on a network density, similarly to the fact that also the Shannon's entropy is defined on a probability distribution, okay? So here, normally the network density in pairwise interaction networks is defined using the Laplacian. Here, what we do is to extend the definition of von Neumann entropy to the higher order Laplacian. Okay, so here is the definition of the of the network density that we use to compute the von Neumann entropy, which is naturally generalized from the let's say standard case in this way. So at each order, so nodes, edges, triangles, and so on, you can compute this quantity, and if the Laplacian is normalized, you are also allowed to compare this quantity at different level of connectivity. Now, here are some results. So these plots show the behavior in log scale of the von Neumann entropy through the collaboration simplicial complex that I've shown you before. Here, the parameter beta, I'm sorry, I did not mention it. The parameter beta here can be interpreted as time, okay? And the study of the variation of the entropy with respect to parameter beta will give an insight of how the information diffuses through the network in time. So here, what you can see is the first row refers to the unweighted version of the network, and the second row refers to the weighted one. In general, of course, we can see that. The dashed line represents the derivative of the entropy. So, which is in physics called the specific heat. And I'm not going to give you much more details about the what specific heat is, because I'm not a physicist and I don't want to go in that world too much. But here the idea is that the behavior of this derivative tells you like the different time scales in the diffusion of information in the network. So, for example, you can see a multi-scale behavior emerging from the entropy computed at order 0, first column, and 1, second column. And this is coherent with the large-scale topology and the mesoscale community. There were a lot of communities, if you remember the graph that I've shown you a few slides before. Of the collaboration simplicial complex. Okay, and so this is coherent with the topology of the network. Instead, at order 2, no multi-scale behavior emerges, and this might be explained in this way. The von Neumann entropy at order 2 reflects the diffusion of information, let's say so, the information flow through the network happening from triangle to triangle via edges, through edges. While in our network, what we have is that most of the triangles are connected to other triangles via single nodes, okay? And this prevents the diffusion between triangles through edges. That is why probably here the diffusion, there is a unique phase in the diffusion of information. Okay, so in conclusion, I introduced a specific convention for the topological weights for studying weighted simplicial complexes that allows to fully access the information about the bare weights that come as input with your higher order interaction data. Then we also went into the specific field of collaboration network, and then we analyzed the bare weight choice that result in the topological weights having the nice property that the sum of the topological weights incident to a node is in fact the total number of papers written by the author corresponding to that node. Another advantage of this choice is that it permits to define a suitable normalization of the Hodge Laplacian that allows to compare topological properties of the simplicial complex at different orders. And finally, we prove this idea by generalizing the notion of von Neumann entropy to higher order networks. Here I concluded my presentation. So thank you for your attention. And if you have any question, please ask. Thank you.
Thank you. Thank you for a very interesting talk. Like, I'm sorry, I didn't previously read very carefully over this paper, but today I got much information from your.
Okay.
Okay. Thank you very much.
I'm happy. I'm happy.
And if there's any question from the audience, just unmute yourself and we can discuss.
Okay, I have some questions. I'm gonna ask one. No. So first of all, amazing. Thank you very much. I already knew it was interesting, but reading the paper carefully, as Anlene was saying, it's hard to do. But it was great, really. So I wanted to ask, like you said, when the network you use like triangles and the Newman weight kind of things. So what I was thinking is, what would change if instead of using like the triangles in each paper, you use like any type of order, like is it 5 authors and then it's a 4 simplex? Would it change, or what would you lose instead? And also, if instead of using that weight, you use like presence or absence, would it change in the results? Like, what's the impact of these two things on the overall thing?
Of course, about the fact that if you use the unweighted version of a network as a start, and then you assign the topological weight, normally the information is different. Okay, so I don't know, probably you have different results in the end, because anyway, like it always happens, assigning weights changes the information at the beginning. So I would say that things change, but I don't know how it changes. Probably depends on the specific problem you're working on. For the first question, actually, this assignment, I've shown the results on triangles because we had very few papers with more than, let's say, 5 authors in our dataset. So for the data we had, it was enough to consider triangles at most. But still, you can consider, you can rebuild the simplicial complex, saying that you are considering a simplicial complex of order 3 or 4 or 5 or whatever, and still this weight assignment works in the same way. Of course, it can be the case that the information content is different in that case, and that would be also an interesting direction to pursue, actually. Yes. I don't know if you have anything to add to this, or if I answered your question.
Yeah, it's something that we still need to check, I guess. Now we can talk maybe privately later to apply this to the problem I'm having now.
Yeah, sure.
Okay, now thank you. I see there is another hand.
Yeah, there's another question. Yeah.
Sorry, I cannot hear. Maybe it's my problem or no. I don't know if I have a connection problem, but
I also cannot hear anything. Yeah.
Okay, because I could not hear anything.
You can put the question in the chat.
Yeah. Yes, very strange. Okay.
Yeah, do you have any oh, okay, I guess his connection
Or maybe he's trying to
yeah, so
maybe he went
reconnect.
and then he comes back.
Yeah, it's back.
Hello?
Okay, now we can hear you.
Okay, sorry.
No,
thank you for your this interesting talk. So I have a question about the parameter beta you were using to define the network density. But I don't know if I missed some knowledge about Hodge Laplacian, but I'm just wondering why we could change the parameter beta to study how the information flows through in the complex systems.
Okay. Yes, actually, it's not trivial. So you did not miss anything. It's not trivial at all. No, actually,
yeah, I just want to.
No, there is if you of course there are some details in the paper, but it can be shown that beta can be interpreted as sort of the average return time a random walker takes to, like, starting from one node to go back to the same node. Okay. So that's the idea behind the fact that beta is time. Okay, so varying beta, you basically varying the time, the average return time of a random walker to a single node. So if you change the length of this walk, it's basically time, and it gives you an idea of the network connectivity and the network structure. And there are some details in the paper anyway. I don't have slides about this, unfortunately, but yeah, that's the idea. I don't know if it's clear.
Yeah, it's clear. Yeah, it's clear to me. Yeah, just say, I will check your paper in detail.
Okay.
For details. Yeah. Thank you.
Okay. Thanks for your question.
Thanks.
Can I ask a last question? No, just very quickly. So from this, I hope. Now, from this representation with the weighted simplicial complex, can you retrieve, like if you store just that and you share that, can you retrieve the bare weights again? I think from the process you use, yes, but yeah, I wanted to.
Yes, because you start from the simplices of maximum order that, if you remember, have topological weight equal to the bare weight.
Yes.
And then instead of summing, you go back and subtract. It's like
I see.
It's
so
exactly the same.
Yeah. So you can retrieve perfectly. And so I see there is a GitHub page there. So I could maybe, like, all the code is there. I can check the code and try for fun.
Yeah, the code is not perfect because I'm not an engineer. And
it's okay.
I'm a very old mathematician, so you can see it from my code, but still it works. So
it's fine.
Right. Before moving on to the next section, can I ask one last
question?
So,
of course.
So basically, I think the idea of comparing the hypergraph and simplicial complexes. So basically, if we want to have a simplicial complex description or representation without losing any information, the basic idea is we just set a zero weight to this simplex, or to these faces that that's not actually present in the data, right? So I'm thinking, like, if we have a in the hypergraph representation, if we have a large hyperedge, for example, we have huge collaboration, like 100 authors doing high energy physics, and so which means you actually need to set a lot of simplex, a lot of phases to 0 to fully recover the original structure using the simplicial complex representation. That's right. If we have a higher order simplicial complex, we will have to put a lot of 0 weight inside too.
No, not. I wouldn't say so. I mean, the problem I see more than that is that if you have a sparse higher order network, so if you have a lot of connections that are 0, then if you choose the weighted simplicial complex representation, the topological weight will be very likely to be non-zero also on those.
Yes.
And so, like there might be also a storage problem in the sense that you have a lot of non-zero edges, while in the hypergraph representation you have 0 edges. But for what you, if I understood correctly, actually, I don't know if that's really an issue, because you just start from the simplices of maximum order. Of course, if you have just one simplex of order 4 or 5, maybe you could think of considering a lower order simplicial complex. No, but okay. I don't know. I have to think a little bit more about it. Maybe we can discuss. You can email me. Yeah.
Yeah. Okay.
I'm not sure if I fully got your point. Just tell me if.
Yeah, I think yes, because later in the Hodge Laplacian, you are actually dealing with this topologically weighted thing, right? Yes, indeed. Then, although we may have many initial weight at 0, but the topological weight will not be 0. Yes, I would agree. Yeah, so which seems to me that will not cause any. I don't know.
No, it's. I mean, in principle, that does not create problems.
Okay. Yeah. Thank you very much. And then shall we move on to the next section?
Okay. Actually, if you allow me, I prepared like a very few slides to introduce the problem. Yeah. If I can share them. I'm still sharing anyway. So, okay. So as you read in the description of this talk, I'm going to give you a little bit some insights about what is a PhD in Italy, and I will talk about mainly some regulations and about rights of a PhD student, and about the few future perspectives. But I'm not going to judge anything I will be open to discussion at the end. So formally, a PhD in Italy is a postgraduate course, the purpose of which is to train a person to acquire the methodological resources to become a researcher, okay? And normally the course is organized either by a single university or by a consortium of 2 or more universities, like mine, because this is regulated by the universities of Pisa, Siena, and Florence. But despite this, it is regulated by a national legislation. At the end of the PhD, of course, you receive a title, the degree of Dottore di Ricerca, and after, of course, a final dissertation. It lasts at least 3 years, and generally 3-4 years, depending on the institution you're doing your PhD in. And the student works under the supervision of a tutor, 1 or more tutors actually, and normally they're professors or researchers working in the same area as you are. So how is the access to PhD studies regulated? So to access a PhD, there's a public notice of competition, and in the period normally between May and September, and the public call is opened by the university hosting the course. There is a very limited number of positions available to each consortium or to each university, normally not much more than 10 positions, with fundings, of course, because there are other positions that I will give you an insight later. So normally a CV and a research proposal are evaluated, and then some suitable candidates are selected to be admitted to an interview. The committee then, after the interviews, compiles a ranking where you can be either a winner with scholarship, meaning that the candidate enters the PhD and is paid a scholarship by the university. You can also win without a scholarship. So the candidate is allowed to join the PhD, but without any fundings. Most of these people choose not to do the PhD anyway, unless they find other fundings, of course. Other people are just eligible, so eligible candidates are able to join the PhD only if some candidate ahead of them in the ranking waits the position. Or, of course, you can be not eligible, meaning that you cannot at all enter the PhD course. So this is how the access works. Once you are in, a crucial aspect is that the PhD is not the same, is not structured in the same way in all the disciplinary areas and in all the university, because some PhDs are very strictly structured. And what I mean is that in these PhD courses, the students have to attend specific number of courses of a specific minimum duration and so on. And this is the case normally for the engineering sciences, computer sciences, mathematics, and such. Other PhDs instead are less strict, and this means that the student does the research full-time, hopefully, because sometimes they exploit you to teach, but this is another story. And they need to submit the thesis at the end of the study. So just the thesis is needed, and then some products in the meantime. Another aspect that makes the PhDs heterogeneous is that some PhD programs can be funded by some companies or industries if they establish some convention with the university. And in this case, the PhD students spend some time working at the host institution. Okay. Now I move to the part of the rights of a PhD student in Italy. As the name says, a PhD student is a student and not an employee. The scholarship indeed is very low for the life cost in Italy. The gross salary is this that you read here, and the net salary is in this one. Just quick notice, at the beginning of my PhD, it was less than this. It was 60 euros less than this. Okay, so in the last year, I was very happy to receive these 60 euros more. As a student, of course, the nice thing is that you have access to all the students' facilities, discounts for public transport, access to university services, and so on. But we are not employees, which could be actually useful from some points of view, because we don't have any 13th month pay, we don't have sick leave, we don't have any annual leave. Fortunately, thanks to the several battles carried on by the Italian Doctoral Students Association, just recently, I think it's a couple of years, yeah, more or less a couple of years, we have the right to receive an unemployment benefit as soon as we finish our PhD, because there's normally a period where you don't have any research contract, or you are looking for something else and you don't have a salary. So we received this 75% of the scholarship approximately, which is a lot, as you can read here. So 896 euros per month, better than nothing anyway. And it is accessible for a maximum of 6 months. What I left in a single slide is the parental leave. So the mother has right to a maternity leave period of 5 months, during which the scholarship is suspended, the doctoral activity, sorry, is suspended, and then you this period that you lose is added at the end as extra time for completing your PhD. So if your PhD is 3 years and you go maternity leave for 5 months, you will have to submit the thesis after 3 years and 5 months from the start of your PhD. During the 5 months, only also here recently, the perceived maternity benefit is the 80% of the scholarship, so 900 per month, which is again better than nothing, but still does not cover the costs of a pregnancy. The parental leave is another thing and is not mandatory. The maximum duration is 6 months, and you receive a lot of money, like the 30% of the scholarship, which is nothing, meaning that, okay, don't go on parental leave at all, it's better. Interesting thing is that once the mother gets back to work, to the PhD, I should not say work, breastfeeding leave is not allowed. Okay, this is a crucial aspect that the associations are fighting on. Now, sorry, these last couple of slides are in Italian, but I've taken them from a yearly report of a consortium about the occupational condition of research doctors. So here, every bar is essentially a disciplinary area. So life sciences, human sciences, and so on. But the focus is on the fact that overall, last bar, who finish the PhD, the PhD students at the end choose the public sector. Okay, so they find occupation in the public sector, which is okay, good. So far, so good. Also, most of them chose to pursue to enter the university. Okay, so the dark blue and the purple are different type of researchers and technicians in the university. So most of the PhD students try to enter the university at the end. But what do they think about their occupations? Let's see this plot. This is a scale from 2 to 10 of the satisfaction level of some aspects of the occupation 1 year after the doctoral degree. And I want to put your attention on the inflections of this plot, which are here: stability and safety of the job, opportunity of contacts with other people abroad, salary perspectives, and finally free time. So the inflections are in fact key points in an occupation, I would say. To conclude, let's suppose we're into the mind of a PhD, which is pretty much me right now. So what do I do after my PhD? When applying for jobs, the PhD degree does not really count as a plus. And we are not usually paid much more than other specialized workers, also in companies or in the public sector. But having a PhD degree is essential if you think about starting a career in academia. So, okay, no, academia is the way. But is it? This slide reports the number of researchers that try to start a researcher career right after the PhD. 62% will not continue to do research. 27% will abandon the research sector after a fixed term contract, a research contract. Other 3% will abandon the research before being able to obtain a teaching position. So in the end, what we have is that in the next few years, just around 6% of the people will be more or less sure to have a, I don't remember how to say it in English, like permanent, okay, permanent contract in the university, while the 93% of the researchers will be out of the research world in the next few years. Here I finish my presentation. I will be curious to know what about the other places and about these aspects I presented. So thanks again for your attention.
Thank you. Thank you very much for providing this information. And I guess you can just feel free to join the discussion. If there's anything you want to say, just unmute yourself.
Just want to break the ice, saying that this is very sad. And I have no words because this is super sad.
Really, given what you said, what are you going to do after your PhD?
Do you have any other questions? Or...
Come back to London.
No.
Yeah, London is nice this time of year.
But what about postdocs in London? Or PhD?
There are postdocs in London.
There's also lots of money for
yeah.
My impression about the post. Sorry.
Yeah. No, just go.
So sorry. I was saying my impression of the PhD in the UK somehow, I don't know if it is right, similar to what you have described. Like the PhD students are still really student in this university, but not employee. And I think I've heard of in some other countries, like in Germany and in Netherlands, some Nordic countries, they are more like employees with its full benefits.
Yes. Yeah.
Wow.
Yeah, I think so. At least I know what I know is about the Netherlands because my brother is there, and yes, they have the same rights as employees, including all the leaves, all the things that I mentioned before. Yes.
So are they taking any courses during the PhD?
Any what, sorry?
Any courses? Do they have to take any courses?
But who? Me, Tahir, or
no,
there?
For the other countries, where students are more like employees rather than students.
Not really, because he's working in philosophy, so I don't know if it changes. In Italy, it changes a lot according to the different disciplinary area. But in there, I think they do not have to attend many courses. I think. Okay.
Interesting to know, because accidentally this afternoon, there is one person I know gave me a call, and she was saying she wants to do a PhD in Europe, and she was asking me like how it is like doing a PhD in Europe. So
oh my god!
It's good to have more
if she wants, yeah. I mean, if he or she or they want to not to make any money, they can come to Italy. You can tell.
In Italy, you need to know Italian to do basically, no? Or some. What do you think about this?
Not in all the courses, I think, because every course in Italy asks. You know that I don't know, because I normally read the regulation for Italian students, and so of course we have to know English, but I don't know about the opposite. I'll have to check. I don't know.
Also,
but I don't think so, because the final discussion, at least for my computer science PhD in Pisa, there are non-Italian speakers and they don't know a word of Italian. And all the courses of my PhD are in English, and the thesis is in English. So yeah, but I'm pretty sure not all the PhD courses are like this.
At least in our fields or related fields, it's good.
Yes.
Also, I was talking, if Silvia remembers as well, we were talking with Sandro. Susa is now in Denmark, I think. Yeah, and he was saying that, like, I think that's the problem in Italy, but the same can be said of all these other countries, that the what you get as a postdoc is basically nothing. Like, it's almost the same as, it's just a little bit more than a PhD, but it's still like at least half or a third than I mean, it's very low compared to any other job that you can do. Like, for example, we can easily do a data analyst job and get double or 3 or 4 times what we get as a postdoc. So yeah, I mean, that's the biggest issue, I think. Instead, like Sandro was saying this, that in there you're basically get the same money that a full professor gets. Or at least there is not such a huge difference between the two parts, and so this is something that we need to sort. I mean, we have to continue fighting, because I mean, it's not something, even if we stay in academia for forever, we're not gonna get a permanent position until like 10 years at least. Especially if we say, okay, like, we want to stay in this country. Let's say you want to stay in Italy, you're going to have a huge problem, because if you are open to have, like, okay, all of Europe, maybe you can find one position that is permanent, like, yeah, like the sweet spot at the sweet time, no? But that's very hard to do. If you have more restriction, you start to have a family or whatever. I mean, you know, it's complicated. I don't know what you think about this, but
yes, I mean, it's like all the thoughts in my head right now, basically. I don't know. I'll decide at some point. I'll decide. No.
What is the point?
I mean, the thing is, I'll try and then see. Because if you plan a lot of things, I don't know, it's very unlikely that you manage to stay in the university. So, I mean, you try and then you see what happens. If you get tired of
see each other in 10 years.
Yes.
I'm gonna have this discussion again.
Yeah.
It sounds like the permanent discussion always happen in the end of like complaining about academia.
Yeah.
I mean, Gabriele, you were saying, Sandra was saying about Denmark, and today and yesterday I Googled a bit about Sweden, and I think it's sort of the same situation. Either the salary, or I don't know about the other details, but the salary, I don't think it's competitive at all comparing to other jobs. And maybe I'm not fully sure, but maybe United States have a little bit higher salary comparing to.
But US is like the NBA of research, and they have a lot of money anyway.
We also have to say that working in academia, so with a postdoc, is not like working in a job that you have to wake up every day at that time and work every day of the week for that amount of hours. So in academia, we have more freedom, right?
But it depends what you do. Because I'm pretty sure if you tell a biologist or some people working
if you
in
work in a lab, maybe it's different. Maybe it's different.
Yes, I think
For
it's
us,
very different.
It's not like that. If you are very theoretical, you can manage your time. You have up and down because you have period that you are working like also in the weekend. And we know, every one of us know that feeling. You have to work also during the weekend. You don't stop. But then you have moments where you are only like, I don't know, collecting results, doing simulations, and then you can go to the beach if you're near the beach. I mean, there are pros and cons as well. Money is for sure a con. But there are some pro also, the fact that you are doing your research, which is not, you are doing something that in principle you like. So
no, I think this is basically the only
this is very nice. Yeah.
And also maybe you feel like you're working for yourself, for the project yourself, maybe the project you're proposing or you're collaborating with.
That's another very big pro if you think.
Yes.
But yeah, it's a compromise. But also with all the compromises, the money sucks in every way always. I don't know. Yeah.
I mean, potentially, yes, because you're doing a postdoc, very possibly that you're not making a very instant and direct contribution, like you're not making any product which can have any commercial profit. So I mean, largely that will be the reason, the salary, which
that depends on the project as well, right?
I mean, if you're working on something commercial, then you may have a higher payment, maybe from the end of the company or whatever. But yes. I don't know if there's anyone from the audience actually, I mean, apart from you, Federica, actually doing PhD now in Italy. It's good to know.
We all escaped.
Yes.
While we could.
But I think today is very nice. Like we have actually 17 people because we have a trial. Even
very successful. Congratulations. It's gonna help finding the best.
It's very interesting. Yes. Oh yes. We need to find a postdoc. Now is the time.
Or something else. I mean, 93%. What was the number?
That was very scary. I always know that the statistics is not so good, but when I see real numbers, oh Jesus.
Yeah. I mean, for me, that was the same effect. Yes.
But that was the number of postdoc, that first number that then splits into the...
Yes, the number of...
So you're not even in that. So you first have to cut into the postdoc part. So that's even smaller proportion of people. Nice.
Yeah.
All right. I think I need to go.
Okay.
Thank you very much.
Let me stop sharing. Stop recording.
Yeah.
Right. Then thank you very much. It will be the very fascinating talk, and it's a very, very good beginning of the Netflix seminar for this semester. Thank you very much.
And please share with us the slides if you can.
Okay. I will.
Good. And we'll see you soon.